Okay. All right. Let's look at a few more things about the pH scale. I think we got one more problem here, and then we're going to move on to buffers. Okay, so what we've learned is that the pH scale is what we call logarithmic. Okay, when we use the log function, we have a logarithmic scale. Here's kind of in layman terms what that means. Let me give you an example. If pH is increased from 6 to 7, the concentration of H plus decreases from 1 times 10 to the minus 6 to 1 times 10 to the minus 7. I'm going to read that again. If pH is increased from a pH value of 6 to 7, H plus concentration decreases from 1 times 10 to the minus 6 to 1 times 10 to the minus 7. Okay, well, how much of a difference is that if we're looking at these numbers right here? How much of a difference is between 1 times 10 to the minus 6 and 1 times 10 to the minus 7? That's like saying this, 0.0000001, 0.0000001. Okay, if you notice there's 5 zeros in the first one, 6, that's a difference of 1 decimal place. So what that means is we have 10 times less H plus. So when a 1-digit change, actually let's read I have it stated perfectly right down here. A 1 pH unit change results in a 10-fold change in the concentration of H plus. Okay, notice we didn't say increase or decrease, we just said change. If you increase pH by 1, you decrease concentration of H plus by 10. If you decrease pH by 1, you increase concentration of H plus by 10. Okay, a 2 pH unit change, then I'm sure you could guess, results in a 100-fold H plus concentration change. This, again, is because it's a logarithmic scale, and we're working on, it works by powers of 10. So if a 2-unit pH change results in a 100-fold, a 1-unit pH change results in 10-fold, what is the result of a 3-unit pH change? And you could probably guess this equals a 1,000-fold change in the concentration of H plus. All right, so knowing what we just talked about, let's look at this problem. We have a problem that says this. Normal blood pH is 7.4. Patients with diabetes and chronic hyperglycemia can have a condition called ketoacidosis where their blood pH becomes too low. Okay. At a pH of about 6.9, a person is in danger of falling into a coma. Yikes. What is the concentration of H plus difference between these pHs, 7.4 and 6.9? So we can look at these pHs and say, wow, that's only a pH difference of 0.5. But in the body, what matters is what's the concentration difference in hydrogen ions. Okay, and I think you're about to be really, really amazed at your body and how good it has to be at maintaining your blood pH. Okay, so the way we are going to solve for this is we are given pH. Remember, to solve for the concentration of H plus, you're going to do 10 to the negative pH. That equals the concentration of H plus. So we're going to do this for pH 7.4. We're going to do the same thing for pH 6.9. We'll get these two concentrations of H plus and we'll just find the difference. Okay, because it says what is the H plus concentration difference? So let's use this equation that I wrote right here, 10 to the negative pH. Let's plug in 7.4 first. So 10 to the negative 7.4. What does that equal? That gives us an H plus concentration of 3.98 times 10 to the minus 8. Times 10 to the minus 8 molar. That's what I got, at least. Okay, now we do 10 to the negative 6.9. That will be a concentration of H plus. That is a value of, I got 1.26 times 10 to the negative 7 molar. And remember, I'm just literally putting this in my calculator. 10 to the power of negative 6.9. And here's what my calculator spits out. So here's our two concentrations of H plus. And we want to know what is the difference between the concentration of H plus for these two pHs. So all we're going to do is, first off, which one's larger, which one's smaller. This one right here, 10 to the minus 7 is larger. 10 to the minus 8 is smaller. So I'm going to do the bigger number minus the smaller number. So we'll do 1.26 times 10 to the minus 7 molar minus 3.98 times 10 to the minus 8 molar. And when I do that, I got 8.62 times 10 to the minus 8 molar. Difference of H plus can cause coma. And instead of difference, we should really say a drop, right? A drop by that amount can cause a coma. And let's think about this value for a second. 8.62 times 10 to the minus 8. That is 0.12345678662. A difference in that amount of H plus can cause your body to fall into a coma. This is amazing to me because our bodies have to be so incredible at regulating the concentration of hydrogen ions in our blood so that we don't die at all times. All right, that's it for pH. One thing I want to mention before I move on, and you may have picked up on this. This may have, some of the wording up here when I was on this slide previous to the problem we just worked, may have been making your head spin. I'm going to write out one relationship that is essential for you to know and memorize for the exam 4. So far, here's some things you need to memorize. Okay, obviously you need to know the equation for Ka and for Kw, but you also need to know that pH equals negative log of H plus. And you need to know that 10 to the negative pH equals the concentration of H plus. Okay? But you need to know this relationship. Okay? The relationship is that as pH goes up, concentration of H plus goes down. And vice versa. As pH goes down, concentration of H plus increases. Okay, they're kind of inverted. As pH goes up, concentration of H plus goes down. The less amount of H plus rolling around, floating around in solution makes things acidic. So the less we have of it, the more basic our pH becomes. But if we have a lot of H plus, high amounts of it, that's what the up arrow indicates, a high concentration of H plus, then our pH is going to drop. It's going to become more acidic. Okay, so know these relationships and know how the concentration of H plus is related to pH. All right, now let's talk about buffers. I think I'm going to pause.